Hi, everybody. We meet once again. Hope you and your families are doing well and everybody is safe as we kind of move through this month of April. We're going to pick up and finish Chapter 4 today. Chapter 4 is entitled Linear Equations in Two Variables. And we've been doing a number of things in Chapter 4. We've graphed an equation using the x and y intercepts and a third point. We have identified the slope of a line by finding all of the different ways the slope can be found. And the most recent discussion has been the equation of the line. And that was the area where we did A, B, C, D, and E, all of those covering the equation of the line. And we're going to finish Chapter 4 today. And it's entitled 4.6, and the title is An Introduction to Functions. Functions are going to be more important in Math 71 if you have to move to that course following this one. Our objective in Math 51 is to just introduce functions and just talk about a few introductory things about this concept. But before we can define the word function, we have to define the word relation. So here's what we mean by a relation. A relation is any collection of ordered pairs where each x value, now here's a brand new vocabulary word, the x value of an overall relation is called the domain. And a relation is any collection of ordered pairs where each x value, called the domain, corresponds to at least one y value. The y value is called the range. So one thing you're going to want to put in the memory bank, the x values of any of the ordered pairs are known as the domain. The y value of each of the given ordered pairs is called the range. Now we're going to start by looking at sort of a real-life collection of ordered pairs that I drew up that I think has a definitive relationship between the domain and the various ranges that they're corresponding to. And this collection of ordered pairs is an example of a relation because, once again, the definition says it is a collection of ordered pairs where each value of the domain corresponds to at least one value of y, which is called the range. Now, this example that I'm showing you up here is an example that has to deal with purchasing gasoline at a gasoline station. The y values, the range values, depict the cost of gasoline. $14, $2.80, $39.20, $28. The cost of gasoline is related to the number of gallons that you put in the tank. So at a particular gas station, if your domain is 5, which would correspond to 5 gallons of gasoline, you're going to pay a range value or a cost of that gasoline to be $14. If you buy 1 gallon, you're going to pay $2.80. If you buy 14 gallons, you're going to pay $39.20. And if you get 10 gallons in the tank, you're going to pay $28. This is an example of a relation. We're also going to find out in a moment that it happens to also be an example of a function, but that'll come in a few minutes. A relation is any collection of ordered pairs where each value of x, called the domain, the 5, the 1, the 14, and the 10, correspond to at least one range value, the cost, the cost, the cost, the cost. This happens to be an example of a relation. Now, one thing that you will be accountable for on the exam, one thing that you will be asked to do is to identify both the domain and the range of a given relation. When we identify the domain, like I just mentioned, the domain is the set of all x values of the given relation. So the x values of this relation dealing with gasoline, the domain is 5, 1, 14, and 10. So when we identify the domain, the thing that you're going to want to remember, it is a set. And when you identify a set, you must use braces. So we begin, when we identify the domain for this relation right here, we begin with a brace, and we simply just identify the x values that we see in that overall relation. The order doesn't matter. After the brace, first domain, 5, comma, 1, comma, 14, comma, 10, comma, or 10, we'll leave it as such, and we close it with a brace. You must remember to use braces. It is wrong if you just list 5, 1, 14, and 10, and you don't include them in braces. The range is the entire set of y values of the relation. So the range would be the set whose members are $14, comma, $2.80, comma, $39.20, comma, $28, close it off with a brace, it is done. You don't need to put the dollar signs. You just list those y values. Very easy to do. Now we're going to go to example number 2. And there's something very important about number 2 that I have not yet stated to you in regards to the definition of a relation. Number 2 is also a collection of ordered pairs in which each value of x, called the domain, corresponds to, here's the key words, corresponds to at least one y value. Here's what we mean by the words at least. We mean that you can have a given x value, the same x value corresponding to two different y values. Let's take a careful look at this collection of ordered pairs. Notice the domain of 12 is corresponding to the range of 58. Let's walk yonder down just a little bit and notice in the third ordered pair, the same domain of 12 is happening to correspond to a different range value of 55. This is okay. This fulfills the definition of relation. Let me say it again. A relation is any collection of ordered pairs where each x value corresponds to at least one y value. At least signifies that you can have the same x value in the overall collection. You can have the same x value, in this case 12, corresponding to two different y values, and it fulfills the definition of a relation. You can see the other pair, and you can see the final pair. This is also a relation. The top one was. This one is as well. The thing that I wanted to point out, you can have an x value appearing more than once. The 12 appeared once here, it appeared once there, and that is fine. Let's look at another way that we can identify a relation. instead of using a literal collection of ordered pairs, we can use what's referred to as maps or mapping. Rule: when you're looking at maps, why are they called that? Because you're looking at configurations of separate little territories that would exhibit maybe a map here and a map here. The map on the left, put it in the memory bank, the map on the left is always the domain. The map on the right is always the range. X first, Y second. Domain, range. Let's look at the domain. It happens to have the domain values of dad, mom, daughter, son, dog. The members of the range, I'll just cue you in on what I had in mind when I drew this up. The range values are not just colors, but they're colors of eyes. The color brown, the color black, the color blue, and the color gray. I want you to take a look at this relationship right here, and what I want you to be able to see from this one, I want you to see a correspondence between the people in a family and their eye color and the previous relation that we had just discussed before, where that domain of 12 appeared twice. Let's look at the family. I'm going to leave dad until the end, folks. Mom. Mom, the value of the domain is corresponding to her eye color of exclusively brown. Each member of the domain corresponds to at least one range value. Mom corresponds to at least one range value. She has brown eyes. Daughter. She corresponds to at least one eye color. She corresponds to brown. Son, the domain, corresponds to at least one eye color. Yes, he does, blue. Dog corresponds to at least one eye color, black. But go to dad. Dad, the domain, not only corresponds to a pigment color of his eye to be blue, but dad, emanating from dad as well, he has a slight little pigmented color of gray. Each value of the domain corresponds to at least one range value. Dad not only corresponds to blue, but dad also has some gray in his color of eye. Dad, the domain, is corresponding to the 12 in this collection of ordered pairs. Dad, blue. Dad, gray. Dad, blue. Dad, gray. At least is key when we're talking about a relation. Now let's go to a function. A function is a special relation. It's a special relation where each value of the domain, x, corresponds to exactly, not at least, but it must correspond to exactly one value of the range known as the y. Each value of domain corresponds to exactly one value of the range. Let's look at two different examples here of a function. Here is a collection of ordered pairs. Notice the domain value of -2 corresponds to exactly one y value called 5. Look down your list of ordered pairs. Nowhere else do you see the domain value of -2 appearing. It's only appearing once. Second, The domain value of 6 is corresponding to exactly one range value 0. Nowhere in this collection do you see the domain of 6 reappearing. It's only appearing once. Same thing here. The domain of 11 is corresponding exactly to negative 12, the range. And 13, the domain is corresponding to exactly one range value, the 5. What is the key to a function? No x value can repeat. The y value can repeat over and over again, but the domain cannot repeat, and it's not repeating here. Let's do the baseball example. In this first map, we have the city names of Los Angeles, San Francisco, New York. The range values, we have the Giants, the Dodgers, and the Yankees. Notice the correspondence. The domain of Los Angeles is corresponding to exactly one range value, Dodgers. San Francisco, the domain, is corresponding to exactly one range value, the Giants. And New York, the domain, is corresponding to exactly one range value, the Yankees. If there would have been the range value of Mets in here, New York would have not only corresponded to the Yankees, but New York would have also corresponded to the Mets. And if it would have been that kind of a case, we wouldn't have a function, we'd have a relation, but we don't have Mets in the range map. An example of a function. Now, folks, before I leave this section, there is a key principle that we want you to know. To have a function, no two different ordered pairs can have the same domain. No two different ordered pairs can have the same x value. Look up here. No domain appeared twice. They each appeared once. Here, no domain appeared twice. They only appeared once. And even back here with the gasoline problem, no domain appeared twice. This was not only a relation, but now we can say this gasoline problem is just as much a function as number 1 and number 2 down here. Over here, these are exclusively relations. These two examples are not functions because the x value, the domain of 12, appeared twice, and in the mapping problem here, dad appeared twice as a domain, and you can't have that. Okay? Now we're going to move over in this area. And we're going to be, for the remaining portion of this section, we're going to emphasize probably the two most important ways that functions can be defined. The first of those two ways, functions can be illustrated by graphs. And I thought I would do this first to make my point. We're going to take a look at this graph right here. The graph is the sideways V that you're looking at. The x and y axes you can see. We're going to take a look at this graph, and I thought the best way to show functions as being able to be illustrated by a graph is to start off with a graph that is not a function. Repeating myself. I thought it would be wise to start off with a graph that is not a function. I want you to look at this graph, and I want you to look specifically at the 2 points that I have placed their ordered pairs beside. This point up here in quadrant 1 is identified by the ordered pair 2, 4. Let me start at the origin so that we're in agreement. 1, 2, that's the x. 1, 2, 3, 4,
There's the y. And then the second ordered pair that I displayed in quadrant 4 is the point 2, negative 1. Back to the origin, x is 2. Y is negative 1. Look at both of those ordered pairs. The statement that I just gave you before I left that previous chart that I was on, to have a function, no two different ordered pairs can have the same domain or x value. These 2 points are on this graph. This point is on the upper portion of the graph. This point is on the bottom portion. Look at the ordered pairs of both of those points and look at their x values. The ordered pair 2, 4 is a completely different ordered pair than 2, negative 1. But look at their x values. The x value, or the domain value of 2, is repeating. Just like Dad repeated, and just like 12 repeated in that other example. The domain value of 2 is repeating itself, and it can't to have a function. This graph represents a relation, but it doesn't illustrate a function, because to have a function, no two different ordered pairs can have the same domain. And these two different ordered pairs have the same domain, and they can't. We're going to share a rule, a test that can be made, that you can apply whenever you're looking at a graph to determine if that graph is a function.